Um, Here, this is the last sections of these chapters, and this is kind of more practical applications of what we have learned. The first one, let me introduce the Saint-Venant Principle. This principle simply is saying that in reality, nearby where the loading is applied, and we should expect the highly concentrated stress here. Okay, that is the very practical issue being talking about here. And away from where the loading applied, for example, if I pick the cross section here, for example, and you should imagine the distribution of the stress become more uniform. Okay, compared to if I pick up the cross section here, and that one you should expect the concentration of the stress will be like this one. So this is not so uniform. So for this phenomenon, because the stress, the highest stress appear seems around where the loading, nearby the loading applied, okay, around this point here. So this is called the stress concentration, okay. The stress concentrations you can see around this point here, okay. Let me show the point here. So around this point, the material point around here, the magnitude of stress is not that big, and away from there that has a smaller stress. So this is called the stress concentrations. And stress concentration is a very practical issue, and what we have learned so far is we so far we take the average, simply is divide magnitude by the area. We simply take the average sense. Okay, this average simply assuming, for example, in any cross section here, and these are cross sections, and in that cross section have an area A, the average stress is like this one. And in schematically, simply average stress for this example simply defined by this magnitude, okay, by this magnitude, okay, so that is the average stress here. So from here you can see our learned the formula, this one is good, but in terms of the estimation, approximation is a very rough estimation compared to the practical one. So the Saint-Venant principle simply remind us we have to do our best to remind ourselves in certain situations we must take care of this such as stress concentrations here. Okay, so so in this quantity here, we provide the ad hoc estimation. Actually, this kind of estimation of the stress, the concentrated stress, concentrated stress, basically to estimate the maximum stress that would occur. And this curve actually can provide a very good job in estimation, can provide a very good approximation of the magnitude of this one, because this curve is obtained by experiment. Okay, they simply the curve fit into the experiment data. So in this way, let me introduce how to calculate this one. The first one, this one, basically this value equal to k, the value obtained from this curve multiplied with the average. Okay, so in this case, the average value, this value is being calculated by our what we have learned, simply divide force, or here is divide P. Okay, divide force by cross-sectional area, and for this case you need to pay attention here. This cross-sectional area is we call the critical cross-sectional area. Basically, given this case, this critical cross-sectional area is the cross-sectional area here. Okay, assuming this width is W, then basically the cross-sectional area, what you're going to calculate equal to W and multiply with D. Okay, the dimension half D plus together is D. Okay, so basically here, let me highlight here that cross-sectional area is this one and plus this one here. Okay, and if you would obtain the A by elsewhere other values, then you kind of failed. In this way, you failed in applying correctly the data here. Okay, so that is the first one. and that is very important. The second one, we learned how to get the value of the K, which is very straightforward. Given this case, we drilled a hole, and we expect the stress concentration will appear around where the material becomes discontinuous. So that is, the stress concentration will happen around the hole here. So given this dimension R and over D, okay, you simply refer to those dimensions. You should be able to calculate this number. From this number, then you can determine what the value of the K is, okay. And so here we have the different, we consider this first case is a hole in the material. The second one we consider is a fillet. And fillet basically is to a way to minimize or reduce the concentrated stress, and depends on the fillet radius, and then depends on the geometry. Then here you need to determine is R over D, and also you need to determine is D over D, and then with the two value you can identify the K. And again, the stress, the concentrated stress maximum equal to K times average, okay, and again the average equal to P divided by, per this definition, is the area here. Okay, always is go to the critical the area, that means the smallest area in throughout the whole material model. So we can look at this example here. So here we are given D equal to 60, and we given smaller d is 40, and we are given r equal to 8. Okay, so here we want to say the allowable stress is 65, so that means this is the allowable stress equal to 165 MPa. And if you remember the allowable stress, that means everything we've been calculated in the maximum stress in the material must be less than or equal to this one to make a safe design. Okay, so that is the design criteria. Whatever the maximum stress happened in this material, there must be under this allowable stress. So under this case, from here the maximum stress is how much? We can calculate is K times average. Okay, so what is the average? So average is simply is P divided by, if you remember, that is the smallest cross section here. Okay, so P divided by this A. And so what is A? And so basically this dimension, this is 10 millimeters thick. So basically A equal to P divided by this dimension 10, and this dimension is 40, 10 by 40 millimeter square. Okay, so basically here since we have everything except the K. So next page we calculate how to determine K here. So here we need to determine R over D, and that is 0.2. So here I will make a line. Then here we need to determine capital D over D is 1.5. So we'll look for the line 1.5 intersecting with here. So that is this value here. So around that value we can approximate that is about 1.5 is this curve here. So that should be here. Okay, so that here is about 1.82. Okay, you can make approximation. If say in the test or in exercise 8, say if I make approximation 1.83 or 1.81, I think that's okay. I won't be so critical about this one. And even if you like, excuse me. A little technical challenge here. Sorry about this kind of the technical challenge, the kind of interruption here. Okay, so here what I mean is even even if you want to approximate k equal to 1.80, I think that's okay. I won't be so critical, and as long as I know you learned the right way. Okay, so right now we have everything here. Then we simply right now we estimated a equal to k equal to 1.80. So basically that meaning is 1.8 maximum equal to the multiply with p over 10 times 40 and millimeter square, and this one less than or equal to 165 MPa. Okay, so from here you should be able to determine the maximum value of the p, and the calculation is here. So the maximum allowable, the force being applied to here, if in safe, must be this value. Okay, this mark the end of these chapters, and for any sections about plastic deformation, I won't cover it in this in this preliminary mechanics material, so I skip all the sections of about this one.